to illustrate this concept of shape and direction of motion being different, let us consider the following interesting example. So we have, again, to recognize the curve. So this would be example 4, I think. So identify the curve, let's say the parametric curve. And it is given by the two equations, x equals to sine t, y equals sine squared of t. And there are no restrictions on t, so it is between minus infinity and infinity. All right, so I should observe that the parameter elimination technique cannot apply, or should not maybe be applied here directly, because it gets rather tedious to express t through x by applying the inverse sign and so on. The easiest way to go about the parameter elimination here is to observe that y is sine squared of t, right? Which is, of course, sine of t squared, like so, right? But since we know that sine of t is x, this is simply x squared. So the shape of our curve is simply that of the very easy parabola y equals x squared. Now the interesting part here, though, it's not the entire parabola, because since x is sine of t, x takes values between -1 and 1. It can never be outside of this interval. So we have a piece of parabola y equals x squared for x between -1 and 1. So that would look like so. We have system of coordinates, and say these are the plus minus 1. And then the parabola looks like so. What our particle, the particle that corresponds to this parametric equation, does is it runs back and forth along this piece of parabola. So as t is increasing, our particle first runs from, so say we start at t being 0, right? T is 0, and when t increases to pi over 2 sine squared of t goes up to 1, goes up this way first, then down to 0 for t going up to pi, and then on to this endpoint, and so the cycle repeats. So the particle corresponding to this parametric equation will traject this little piece of parabola back and forth as t increases or decreases, and it will be 2 pi periodic motion, in the sense that if you think of t as time, then every 2 pi units of time this particle will return to the same location. But it will not, however, be the entire parabola y equals x squared. So this is another instance where parameter elimination is much easier if you just observe by looking directly at the expressions for x and y that y can be expressed through x. So here it is much easier to do it this way than to express t through x first and substitute that into y. So for comparison, the approach that we applied previously here would give us something like this. We would first express t through x, and then substitute it into y. So we would have something horrible like this. And so this requires some thinking about how this composition can be simplified, whereas what we did here was much more direct. We just had to observe that, hey, y is sine of t squared, and that's precisely what you get if you square x. So noticing this dependence directly was much more easy, was much easier.